Good morning, everybody, and welcome to the second week of Astronomy 120. This is the late start session, so this is slightly different than the first one. This is section 71. So this is a follow-up on the first week that we have last time. I know that a lot of you are probably going to watch this recording later because the attendance is not as high as it is, and that's because, understandably, because the class is an online class and you're not required to attend it live. However, as I said before, you really need to watch the recording then, in this case, if you cannot make it live. The reason why is because a lot of assignments depend on that. So you must watch the recording then because you cannot attend it live. So the first week we covered basically unit 5. Today we're going to build on that, and we have several units actually to go through. We have units 6, 7, 8, and 9 to finish by the end of the week. So we have quite a busy week, so we really need to get started on it. Also, let me share the screen in here. Let me find it first. And let me change to the student view. And let me share the screen. Again, what we have this week is similar to last week in a sense that we have most of the stuff that is similar to what happened last week, namely the objectives from this week, the content, where there are some relevant content in here. The discussion this week is due the 23rd. One of the things that I always point out to you guys in here is that the objectives not only lists the objective, but also what is due in terms of this week. Obviously, we have the discussion from the week before. We have the assignment that was started last week, and that is important that you guys have to complete it by, the first part has to be done by Wednesday this week, and then the final part, which is the reply to the peers, has to be done by the 17th. So you guys really need to adhere to that because this would determine whether or not you're going to remain in class or not. So please take care of all of these assignments and make sure you participate in the class. This week's assignment is actually due on the 23rd, which means next Friday. And then you also have a quiz from this week that is actually going to be due next week on Tuesday. So again, you guys need to follow this objectives as they are very helpful for you guys. So let me go back in here. So again, the units that we need to make sure that we're covering is from last week to make sure that we finish that. And also we have several units this week. So the number of units that we'll be covering on a weekly basis depend on the load. Sometimes we'll only have one unit, sometimes we'll have more. Down the road, you will have more assignments. Okay, so this is the first time we're gonna see a quiz. And it's a timed quiz, so go through. Then again, like last time, the discussion of the live sessions after they're recorded, they're going to be posted toward the bottom. Okay, so let me stop sharing that, and let me go into the PowerPoint. Make sure that I have Unit 6 in here. Share. Again, this is from last week. Basically, one of the things that is part of the objectives then was to describe the annual motion of the sun. And what do we call the dates when the sun reaches its extremum points? Those are important dates, basically 4 dates in the year, namely December 21st, March 21st, June 20th, and then September 21st. Those are the winter solstice, the spring equinox, the summer solstice, and the fall equinox. Okay, define the ecliptic and the signs of the zodiac. These are the things that we talked about last time actually extensively, namely depending on the position of the sun versus us and how we see the night on that time of the year. For example, on August 1st, we can clearly see Capricornus right in the middle of the sky. And then Sagittarius and Aquarius will be on the other side of the sky. But again, they move, okay? The Earth is spinning, remember, it does one rotation every 24 hours, basically. And then that is the night sky. But we cannot see, for example, Cancer or the Gemini or Leo because they are on the opposite side. When we are 6 months later on the other side of the sun, then those become visible, and the ones that are visible on August 1st, they will not. So that's because of the motion of the Earth around the sun, and those are the signs of the zodiac. The path through which the sun apparently moves in the sky, that is actually called the ecliptic, as it's depicted in here. And the ecliptic passes by all the signs of the zodiac, and that's basically, there are 12 of them, and that is what we see. Unless there is a solar eclipse, where the sun is hidden a little bit of view for a little bit, then we can't see the constellations that are on the other side of the sun, because they will be during daytime, and daytime the sun basically overshadows everything in here, so we cannot see that. So again, this is an annual motion, repeats every year. Because of the tilt of the Earth, that has actually an immediate impact. The Earth is slightly tilted. It's not exactly. Let me see if I can get something in here to illustrate the point. Let me take this pen in here. Okay, so this is the ecliptic. My hand in here is the ecliptic, and this is basically the orientation of the Earth axis from pole to pole, from the South Pole to the North Pole. This is not a 90 degree. As a matter of fact, it's off a little over this angle. So from where it could have done a 90 degree, off by 23.5 degrees. So this tilt has dramatic impact on the seasons on the Earth as the Earth goes around the sun on a yearly basis. Okay, if it were not for it, we would not see the seasons the way that we see them. So again, from this picture in here, the Earth is tilted. The North Pole and South Pole do not point in the plane that is perpendicular to the plane where the Earth moves around the sun, okay, by an angle of 23.5 degrees. This angle actually fluctuates a little on and off of 23.5 degrees. So it can go as far as 25 and then as slow as 22. So this depends on the also part of it. So if it goes 25, that means the seasons will be far more extreme. The cold becomes a lot colder and the hot becomes a lot hotter. But if it gets closer to the ecliptic, actually, to the normal to the ecliptic, by the angle becomes smaller, then the seasons become less extreme. And as a matter of fact, the cold seasons become less colder and the hot seasons become less hotter. So the temperature becomes more moderate, if you want to call it that way. That is basically the effects of the tilt of the Earth, okay? Again, it's the inclination that causes the seasons, and it's also those are the important dates I was talking about in here. March 20th, actually, and June 21st, they fluctuate these dates a little bit on and off, okay? With a few hours left and right, okay? Because that's when the season, when the Earth passes through those basically dates. Again, the Earth is at its closest. Sorry about the noise, guys. I'm sorry about that, okay? I'm trying to get it to stop, okay? Until now, my office is not ready, and I'm trying to basically do something in here in such a way that we will have a class. Anyway, the point being in here is that the seasons in here, they have to do with the position of, at least these dates, they have to do with the position of the Earth around the sun. The Earth is in the closest approach, actually on June 21st, and then it's furthest around December 21st. And then as it moves around, remember the path is not really a full circular path. That's why there is a kind of an elongation a little bit on one side or the other. So why is the summer hotter and the winter colder? It has nothing to do with how far the sun is from the Earth and vice versa. It has to do only with that tilt. As a matter of fact, if it was a distance, the December should be hotter than June because of the proximity of the Earth from the sun. So it's actually the tilt of the Earth, that 23.5 degrees, that makes a difference between summer and winter, okay? And here is the reason why. If the Earth is tilted toward the sun, like for us, for example, in the northern hemisphere, when it's summer, then we will receive the bulk of the radiation. The sun will become immediately above our heads, versus the southern hemisphere where the sun comes at an angle, tilted angle. So the rays of the sun will have to travel through the atmosphere, but a much longer atmosphere in the southern hemisphere than they do in here, because they're directly above us. So they travel just a cut across and they are on the surface of the Earth. So the Earth receives more radiation because of this angle. Not only that, the day lasts longer in this case in the northern hemisphere than in southern hemisphere. So not only the light is more exposed, I mean, the radiation is coming straight up, meaning that it travels less and gets straight to us, but also stays longer, meaning heating the ground even longer and longer, causing even warmer temperatures. That's why we have summer in here. In the winter, it's the opposite direction. The Earth will be pointing in such a way, if you think of my left screen in here, that the sun is coming from the opposite direction. So the rays will be more exposed. Remember the equator in here, that line in here, that divides the Earth into a northern hemisphere and southern hemisphere. So the southern hemisphere in this case will be exposed directly to the sun, whereas we will have that angle. And it takes less time for us to stay exposed to the sun. So there is less time, and the angle also is tilted. So what causes the seasons on Earth? It's not the distance from the sun, at least. That has nothing to do with it. Actually, the minor implication, if you wish. It's very, very, very secondary. It's negligible to the point that you don't talk about it. What matters is this tilt of 23.5 degrees, okay? And this is true when it's our summer in here, it's their winter in there, and vice versa. When they have their summer, we will have our winter because of this tilt. Because remember, the Earth does 12 months a year around the sun. So 6 months in here and 6 months in the opposite direction. And then there are the transition times when the sun will be directly on the equator on both sides. And that could be either spring if we're coming from winter, or could be the fall if we're coming from the summer in our region, and vice versa in the southern hemisphere. Again, this is the Earth during the summertime in here, because the tilt is toward the north. And this is the Earth during the winter time. Okay, the winter time, our winter time in here, the sun is actually hitting more the southern hemisphere than the northern hemisphere. The sun's path is on the ecliptic, as you can clearly see from the second picture, but the Earth is tilted by 23.5 degrees from the ecliptic. This angle is 23.5 degrees. So in the summer, on the solstice, the summer is actually coming, the sun is coming straight up to the northern hemisphere and vice versa. So if you're asked ever about what causes seasons, it's the tilt of the Earth, not anything else, okay? The equinox is the summer, the sun passes through, I mean, the two planes meet. The ecliptic plane and the equator, they meet together. And that is when the daylight and the nighttime will be the same length, okay? And that is the most moderate time in the year. Now, depending on the year, if this is the celestial equator, what is celestial equator from our previous unit is that basically the projection of the Earth's equator on the sky. So the projection of the Earth's equator on the sky, the sun can go as low as the 23.5 degrees away from it in the winter. So basically rises, doesn't spend much time, and sets. In the summer, it rises and keeps on rising and rising, and takes a long time before it comes down. For an observer like this, like us in here, there is the sun is very high in the sky in the summer, and it's not that high in the sky in the winter, provided the same time. In the solstice, these are in the solstices, but in the equinoxes, it's going to be in the middle, because it has transition between all of this region throughout the entire year. So if it's right now, we are just past the equinox, the spring equinox. We're continuing toward, I'm sorry, in the opposite direction. We're going toward the winter solstice, and then we're going to travel back toward the spring equinox, and then toward the summer solstice, and vice versa. We'll travel back again toward the fall equinox, and so on and so forth. Okay. So this is, in a sense, what's going on. So the sun rises or sets in different locations in the sky, okay? On December 21st, the equinoxes and so on and so forth, and this is to the north, okay, where it sets. So the summer is going to set it's going to set further in the north and rise further in the north, and in the winter it's going to set further in south, and in the solstice, in the equinox is going to go straight east-west. So again, this is the path of the sun as the Earth is spinning, okay? And this is its path from time to time. Okay, if you look due north, and I'm looking due north actually where I'm sitting right now, I'm looking at the San Bernardino Mountains. If you look due north and draw an imaginary line to your due south, immediately behind you, passing by the point immediately above you, that is your zenith, that is actually your local meridian, okay? Where the sun passes by your local meridian is what we know as noon. And that motion actually changes from time to time on the year round. Okay, there is another motion that we have to take into account in here when we're talking about the sun, and that is the precession of this tilt. Remember, the Earth is tilted by 23.5 degrees, but it's not always pointing to the North Star. It's not always pointing to Polaris. Okay. Today, it's pointing to Polaris. So if you go out at night and look at the north and raise your hand about 23.5 degrees, that is actually where Polaris is. It's the other end, basically the end of this Ursa Minor, which is the Little Dipper. So if you look at the Little Dipper and think of it as a pot, the handle of the pot toward the end of it is where the Polaris is located. So that is where the north is pointing. In other words, the north from the Earth is pointing to that star. But for a cycle of about 26,000 years, that direction changes. About 4,000 before our current era, it was Thuban that was actually in the northern the northern star. So it's not Polaris. So this changes. And if we move 14,000 years from the current era, that is actually, we have to move in the opposite direction. No, actually, yeah. It doesn't matter because it's a cycle of rotation. It repeats anyway, every 26,000 years. Vega was close from, but not actually the northern star. But if you're trying to find where your north is, that is where you have to look. You look at the constellation Lyra, and that's where the Vega is going to be. Vega actually is not going to stay in its location on the same night. Because remember, Polaris stays in its night. So if you take a long exposure picture of the night sky, you will see all of the stars revolving, all of the stars going in circles around Polaris, with the exception of Polaris that hardly moves, budges from its place. But in part of the cycle when Vega actually is going to make a circle, but a small circle nonetheless. And it's going to be our northern star. And sometimes we will not have a northern star at all. And this is similar to the current situation right now with the southern hemisphere, where they don't have a southern hemisphere, if you wish, star, the equivalent to Polaris in the southern hemisphere. They have actually an asterism, and that asterism helps them find where the south is. So basically, this is some of the useful information that you have to know, is that this cycle repeats every 26,000 years. Apparently, it has drastic implications, at least when the Earth was pointing in another direction. Apparently, the modern Sahara was not that desert at all. It was a fully lush region, similar to basically other regions that have a lot of vegetations and things like that. So, and rivers and things like that. So this has implications, at least according to some of the hypotheses out there about the weather on Earth. This cycle is a very long cycle though, okay? 26,000 years. There is another, this is part of what is known as the Milankovitch cycles. And there are a bunch of them that has to do with the precession of the Earth, and also that also has to do with the eccentricity of the path of the Earth. Sometimes it's a little bit more eccentric, meaning that actually the distance starts to matter then. Okay, the further away from the sun, especially if it's tilted in the opposite direction, the longer the nights and the colder the nights are, and the colder the winters are, and the hotter the summers are, and so on and so forth. So it has some kind of complicated implications. That cycle is about 100,000 years, though, not 26 like this one. So again, This is the motion of the Earth around the sun. Let me open the second one in here, which is from Unit 7, which is actually from this week's notes now. Unit 7 deals with the day, and we will have a lab specifically on this one in here. Okay, and this lab is actually due this, so we should have it this week, where we're going to talk about the motion of the sun around the Earth and how the day is defined and so on and so forth. And we're going to define different day. So again, we're trying to define the day, and there is a problem now when we define the day. How are we going to define the day? One of the things that we could think of is from sun rising to sun coming back again and rise again the next day. It has to be a repetitive motion somehow. But there was a difficulty, as we were saying earlier, depending on the time of the year, the sun will rise further to the north if it's summer, and further to the south if it's winter. So the location of where it rises is complicated a little bit, and the day becomes a little bit confusing. There is also the sunset. There is all kinds of other issues there. But the common method that is adopted is that if you look at the sky, just above your meridian, your local meridian, your own, not that of somebody else, okay, not that of the prime meridian, for example, which is the where we start measuring the angles for the longitude. No, your local meridian, namely, you look due north from where Polaris is. Immediately behind you is due south. That is the point. Then you draw a line in the sky, in the celestial sphere, and that line must pass by your zenith, because there are a bunch of ways of drawing a line going to you behind you when you are on a sphere. The line that we're talking about is the one that passes immediately above you. That is your local meridian. Now, when the sun crosses that line, that is noon. Part of the lab, you will see that noon has nothing to do with 12 p.m. or 12. Yeah, it's not exactly 12 p.m. for our location. Planet X is off by an hour or so, depending on the time of the year. So that is your noon. So the noon is exactly when you have the least amount of shadow, depending on the time of the year. If we happen to live, for example, in a zone below the 23.5 degrees, we would have times of the year when the sun is immediately above our heads. Then we will have no shadow. Similar to Cyan, in southern Egypt, which is in that region. So at some points of the year around the, excuse me, the summer solstice, you will have no shadows. Objects will have no shadows. But because we are a little above that, we are at 34 degrees, therefore we cannot have that. But the transition between the shadow from one direction to the other direction, that is your noon, actually. That's another way of looking at it, okay? The sun rises in the east, so your shadow is on the west in the morning, and the sun sets in the west, so your shadow is on the east. Where it transitions between west and east, that is actually your noon. And it's going to be the smallest amount on noon, because we cannot have 0-degree shadows in our region. The point being in here, that is your noon. Now, you wait until the next noon, which is the day after, the same situation, and you call that 24 hours. So that is a convention. We decided that that is our day, is 24 hours, because we like to divide the day into two different portions. Each one of them is 12. So a day-night, we call it 12 hours, and daytime, which we call it 12 hours. But the daytime and day-night are not actually 12 hours each, unless you are in the spring equinox or the fall equinox. They will not. So in the winter, the day is less than 12 hours, the daytime that is, and the nighttime in the summer is less than 12 hours. So pick and choose. So basically, you understand the point in here. Excuse me. So that is what we call the solar day. This is how we define the day based on the sun. However, there is another day that is equally important, and that is the actual rotation of the Earth around its axis. It's not 24 hours. It's less than that. Okay. Why? Because the Earth is going around the sun in the same time as it's spinning around its own axis. So the actual rotation takes less time than the actual, agreed on day. We call the second which is proper rotation of the Earth around the sun. That is what the sidereal day is. That is the rotation of the Earth with respect to the background stars. And our locations in here. Let me guys ask you a question, because I'm kind of seeing something that popped up on my screen in here, which is kind of strange. You guys lost the camera? Can you guys hear me?
Yes.
Yes.
Yeah.
For some reason, my camera now is turned off. And I've had this problem earlier in the day. So if for some reason this thing hangs, please don't leave, okay? I will come back and basically restart it and continue, okay? So let me continue with this unit in here. So again, depending on the location, you might end up with a situation where you could have no day or time, no daytime, that is. You still have a day, and no nighttime, depending on the time or location. But for us in here, in our latitude of 34 degrees, we will have day and time all the time, okay? Day, night, and nighttime, that's what I meant. Okay, this is what I was talking about in here, and it's very important to understand this point because it has to do a lot with the lab. Okay, 24 hours really is what I call noon to noon. Remember, passing through the prime meridian, sorry, not the prime, my meridian is noon. The next noon is when it passes again through my meridian, not anybody's else. So I'm standing in here, looking at the sun, and wait for the next time when the Earth goes around, makes a full circle, so that I'm looking at the sun again, immediately above my head. But if I'm looking at the sun, the Earth actually spinning around its axis, I was looking at the background stars, for example, if there is a solar eclipse. If I'm looking at the constellations in this case, and I could look at the constellation in this direction, I'll obviously do that too. So I could start calling a daytime from when a star passes through my meridian until the next time that same star passes through my meridian. That's the same thing. I will find that that time it takes is actually less than 24 hours. It's 23 hours and 56 minutes. Okay. So what happened in this case, because the Earth is actually moving around the sun, it takes 365 days to complete a full cycle. So basically, I need to catch up with that extra distance of 4 minutes to make up for that difference, so that the Earth will spin a little longer to catch up the sun in the position where it's in the meridian, when it's in my meridian. That's why the solar day is always longer for the case of the Earth than the sidereal day. And it's true always when an object moving in the same direction is spinning in the same direction. But the case of Venus, and please pay attention to that when we come to Venus, Venus is actually spinning in the opposite direction. The sun rises in the west and sets in the east for the case of Venus, and moving in the same direction as the Earth is. So because of that, the sidereal day, or the sidereal day and the solar day are completely different, and they have different calculations altogether. So we need to come back to that one, but we're going to cover that when we come to Venus, okay? But this distinction is very important, and it's coming in handy later on when we talk about the lunar month also. The lunar month is from when the moon is new to when the moon is new, or if you wish, from when the moon is full to when the moon is full. So that is a lunar month that we decided, and we measured it to be 29.5 days. When we actually compare the moon's location to versus the background constellations and the stars, it takes only 27.3 days, meaning that it's about 2 days short. So that is the sidereal lunar month, which is 2 days short than the lunar month that we agreed on, okay? That has to do also with the rotation of the Earth, because the moon going around the Earth, and the Earth is moving around the sun. So the moon has to make an extra, basically, motion to catch up with its position versus the background constellation, so that we call it a lunar month. Okay. Sorry, did I say that? No, it's the other way around. It's going to catch up to the same constellations, but needs to make an extra distance so that it can catch up with its own phase. because we decide the lunar month on the phases, not on its position with respect to the constellations. Same thing in here. The sidereal day has to do with the position of the Earth with respect to the background stars. So in this picture here, you can see clearly these arrows, the blue arrows are pointing to where the stars are. And they are parallel to one another because the stars are far away to see any kind of distortions with them. So they are parallel lines. Versus the sun, which needs that extra push to make for the sidereal, to make up for the solar day. Okay. Again, I mentioned already that the daytime and nighttime change depending on your location, depending on how far you are, depending also on your season. Okay. Sometimes, for example, the day can be as long as 13.7 on the equator. It's going to be exactly 12, and then it's shorter. The daytime is shorter in the lower hemisphere, and then the whole thing flips when it's winter in our case. Okay, so again, daytime is shorter in the case of winter, 10.3 hours in this location, and it's longer, 13.7 hours when it's summer. So again, that is something that we know. And that's what created what is known as daylight time-saving zones. Because here is the thing. First of all, the time zones. Because of the rotation of the Earth, and it has to be rotating, and it has to have that spherical shape. And because we decide that this is the prime meridian, the one that passes through the city of Greenwich, okay? And it's the zone that has this yellow region. That is the prime meridian zone. So, and you can clearly see from the geometry, the prime meridian passes through France, parts of Spain, Algeria, and some other places, yet they're not on the same time zone as Greenwich itself, and some of the other countries that don't even have the prime meridian passing through them. And actually, they have the next hour. If you extend this hour, it's passing through, for example, parts of Morocco and then also Mauritania and some other places. So technically, there is a shift in here. So here is, first of all, the different zones in here in this region. So you have the 0 hour starting from here and comes back all the way to the international line in here. So you have from 11 before the prime meridian to 12 behind the prime meridian. And this is the international. This is what decides to be tomorrow versus today. This is what decides to be, if you are on one zone, the day started, and here behind them, they are still in tomorrow and yesterday. So that is basically the distinction. Or here, we're still in today, for example, in the islands of Hawaii versus the next islands, which are actually in tomorrow. So this is the international dateline that determines the transition from days to days. And this is the one that determines the location with respect to the prime meridian. Again, if you take 360 degrees, and let me share with you the screen because it's important that you guys see the, what happened to the calculator over here? And I lost it somewhere. I'm sorry, I was trying to grab oh, it's in here in front of me. I'm sorry. I was trying to share with you something in here. Sorry, guys. I know you're not looking at me. For some reason, my camera is not working right now. And I probably should close this thing in here. It's useless anyway. Probably have to invest in one. So let me share. Now, before I share, let me prepare it first. Now let me share. Okay, we're actually in the second part, so I guess we should call it week 2, maybe. Are you guys looking at this screen in here from my OneNote? Yes, no, maybe. Can put it in the chat. You guys, can you hear me first or not?
Yes.
Okay, are you, do you see my OneNote or not?
Yes.
Very good, thank you very much. Okay, so the idea is the following. So here is the point. First of all, we decided that here is Greenwich. That's what we decided to be 0 degrees. Okay, that is what 0 degrees, and that is actually the prime meridian. Okay, so we're going to go full 360 degrees and come back to it. That's how the Earth is shaped. So instead of dividing it into 360 degrees, which is what it should be in degrees, we decided to divide it into 24 hours. Those are the time zones. Okay. So 24 hours, not degrees, I'm sorry. So how many degrees does an hour correspond to? So 1 hour would correspond to basically 24 hours for 360 degrees. Okay. That is basically what the whole idea is. In other words, did I do it backward? Yeah, that's basically what the whole point in here is. So in here I have 1 hour. I should have it one in here, 1 hour. My question is how many degrees that is. That's really the whole point in here. How many degrees will correspond for 1 hour? That's the whole thing in here, because 24 hours will correspond to that, okay? Or I should put it in a simpler relationships, 360 degrees will correspond to 24 hours. How many degrees would correspond to 1 hour? Okay, if I take 1 hour times 360 degrees divided by 24 hours, that should give me the number of degrees. So the number of degrees, I know the book gives you the answer, but I'll give you the rationale behind what how you find that. So it's 360 times 1 hour. So this is degrees, this is the hour, and this is 24 hours. Okay, so that's actually the proper math in here. So the point is the hour cancels the hour and the answer will be in degrees. If you take 360 using your calculator and you divide it by 24, the answer is 15. So that's how we ended up with 15 degrees. So 15 degrees would correspond to a 1 hour of difference. So between us, for example, and Arizona right now, it's the same time zone. But for example, New Mexico, it's at least there is one time zone. So you're asking roughly how many degrees that is, roughly, because it could be longer. Because if you are in the beginning of the time zone, you have to be in the beginning of the other time zone. If you are in the end of this time zone, you have to be in the end of the other time zone to count 15 degrees. But if you are at the beginning of this end, this time zone, and you're looking at the end of the other one, obviously the difference is less. If you are at the end of this time zone, and you are at the beginning of the other time zone, so it's different. But we agreed that the entire time zone will have the same clock. In other words, people on the beach, for example, will have the same time as people, for example, living in the border with Arizona. Obviously, that's a big distance. That's about 200 miles. And 200 miles is a few degrees. So you ask how much we have to travel in order to, is it 200? Yeah, it's about 200. So you have to ask how long do you have to travel to completely full cover 15 degrees? And the answer to that is the circumference of the Earth is about 40,000 kilometers. So in a similar fashion, I could take 40,000 and divide it by 24, and that should give me how much it takes to go 1 full hour, okay, on this whole distance. So again, if I take 40,000, and you divide it by, let me use a calculator quickly in here. This is in kilometers. The answer is not going to be in miles though, because I did the whole thing in kilometers. So 40,000 divided by 24. And the answer, of course, is 1,666.7 or whatever. So it's roughly, okay, it's about 1,700 kilometers. You ask how many miles that is? It's about 1,000 miles. That's the distance you have to cover in order to go from one time zone to another time zone, okay? So that is basically the distance you have to cover. And that has immediate implications because I'm gonna ask you guys, what is the time right now in New York? Does anybody know? Right now, in our time zone, the time is 11:21 a.m. Does anybody know?
2:21 p.m.
2:21 p.m. Okay, actually, you can Google it. You can just go there and it's going to give you the time. PM. Very good. So there is a delay of how much? 3 hours. So if somebody asks you the distance from where we are to the time zone of where they are, what is the difference? For every hour, it's about 1,000 miles. So how much the distance is going to be from coast to coast?
About 3,000 miles.
Yes, exactly. Okay. Here is the difficulty, though. It's not usually exactly actually when I drove, I think last winter, to Virginia Beach from where I am at, which is Loma Linda Redlands area. It, according to my car, it was like 2,700 miles. So it's not exactly 3,000 miles, okay? Because you could end up with a little less or a little more. And there is a reason for it, because the time zones have something to do with the geography. They have to do also with the politics. That's why they are not exactly straight lines, okay? So the United States, there is a -5, it's 5 hours behind Greenwich time, the Eastern Coast, and we are 8 hours behind Greenwich time. So if you ask how many degrees 8 hours are, 8 hours times 15. So you can find how many degrees that is. 8 times 15. 8 times 15. Come on, it's not coming up. Oh no, that's not what I want. Did anybody have any access to a calculator? 8 times 15. It's 120 degrees. So between us and Greenwich time, it's 120 degrees. It's important to remember this number when we do the, there is a problem in one of the homework assignments about how to predict the next lunar eclipse. And it uses actually this same math, okay, that I'm showing you. You multiply 8 hours, our time zone, versus that of Greenwich, and you make a prediction where and when is going to have the next lunar eclipse. Again, it has to do with all of this kind of math, which is a little bit sometimes challenging, but I'm hoping that you guys understand. So what matters in this case, look at, for example, the date line in here. It zigzags between the United States and Asia, between Alaska and Russia in here. And then it goes through kind of a pattern, and then all of a sudden it squeezes itself all the way 2 time zones below, and then comes back. It has to do with the politics, it has to do with the same countries basically wanting to be in the same time so that they refer to each other and so on and so forth. But that creates a problem, because it could be setting, the sun could be setting at 2 o'clock or 3 o'clock in the afternoon. And that's an issue in here, but that's basically, they want it that way. The United States decided to divide itself into these different time zones. And each time zone, of course, the sun will set a little bit earlier in the eastern part of the same time zone than in the western part of the same time zone. So there is a little bit of politics involved. There is all kinds of other things also involved. Now, because of the day that is being there shorter in the winter and longer in the summer, some places adopted the daylight saving time, and actually other places in here, they adopted the different kind. The summer daylight savings times is observed in a different fashion, and those on the southern hemisphere. Not everybody does that, though, as you can clearly see. Yes, Europe and parts of Asia, and actually Morocco and Africa, and what is this? Also, the United States, and some states like Arizona, for example, doesn't care about the time zone. If you happen to drive to Arizona, sometimes they will be on our same time zone, and sometimes will be behind, and that's basically the thing that we did. So where is the idea coming from? Again, it's coming from the point that, listen, because the sun actually stays longer during daytime, and it doesn't make sense that we're going to basically turn on the lights for the evening, for the street lights at a given time when it still has plenty of light in that region. Okay, so that is really the idea behind it, and that's how we we adopted this convention here to save energy and to save things like that. Okay. Okay, I'm sorry about Canvas. Apparently, it's giving me this headache in here today. It's not Canvas, actually. Zoom is the problem. And Zoom has not another problem. I believe now it's my camera because it's been doing this from before. It's kind of hangs. If I unplug it and plug it back, it's going to work. Let me check that quickly here while we have this. Oh, did I unplug the sound? I'm sorry. Didn't work still. Okay. You guys can still hear me?
We can hear you, not the screen.
Yeah, it's really the trace down the wire. What's this? Okay, so apparently it's still giving this thing in here. Oh, when it went out and came back, apparently I needed. It says I don't know what that the camera was pointing to. It was supposed to be this camera. Anyway, sorry about this disruption in the problem. There's the thing that happened in here. So I want deliberately to leave the unit for the other two units, namely 8 and 9, together, because they're kind of very important to discuss them, especially unit 8 itself by itself. It has to do with the lunar phases. You will have a project not too long from now. So you will have a project where you will go out on 4 nights actually to observe the position of the moon, the shape of the moon. And when I say position, I don't mean exact position. I don't mean to give me it's basically right ascension or declination or anything like that. I don't mean to give me the angular measurements, if you wish, the azimuthal angle and whatever you want. No, you just want an approximate position. So if you're looking at the southern hemisphere, for example, and the moon is on the southern hemisphere, close from the horizon or above, well above the horizon, close from your zenith, or if it's toward the east or toward the west, toward where the sun is setting, or toward the sun where it's supposed to be rising, because you're going to be looking at it at different times. It could be in the morning, early in the morning, or early in the evening, or late in the evening. Those are the times basically that you're supposed to be monitoring the moon. You're going to document the date, you're going to document the time, you're going to document your location overall. I am in San Bernardino, for example, or I am in Redlands, or I am in Rialto, it doesn't matter where you are, roughly, okay? And then, although all of these regions are more or less the same region, because they all have the same, more or less the same latitude. I mean, the fractions of an arcsecond here and there doesn't matter really much. But unless you are probably somewhere else in California or even out of state, then I really need that information, because it's going to make a difference. It's going to matter a lot for your observations. Your observation will be different. So, and then in your location, then you're going to describe the shape of the moon. How does it look to you? Describe it physically, and then name the phase of the moon. So unit 8 will come in handy, because it's going to teach us about the phase and which direction the part that is lit and which direction the part that is basically hidden from us, okay? So that is the project, and then you're going to draw it and you're going to answer a few other questions. So that's the project. It has to be done over a 4-week span. The observations, you have to do them over a 4-week span, and you'll be given specific dates when you're going to go and look for it. Now, if the weather doesn't permit, like for example, yesterday it was too cloudy, you can't see anything in the sky, then in this case, you have to wait the next day. Or if you know the weatherman is telling you that on the date when we are planning our observation, the weather is not good, then you have to go the day before. And you have to go the day before anyway do spotting. You're going to go and try to find, oh, where is it supposed to be, so that when it comes the observation, you're going to do your observation in duly in the proper place, and you take note of it and everything else. Remember, this assignment is graded, and it plays actually a major role in your grade, so you have to take it seriously, and you have to do all of the steps on it. The first part is observation. The second part is actually submitting your reports of the observations, including your sketches and including your reports and things like that. And that is why I'm kind of emphasizing on Unit 8, because it will have a major implications on this project. So I want that to be part of the Wednesday discussion. Of course, Unit 9 actually delves into the calendar. Calendars are something that really evolved over time to the day when we have now the calendar. So what we mean by calendar is how do we keep track of dates, and there are different kinds of ways. The two main ways that are actually known today are either the Gregorian calendar, which is what we use today, basically the calendar that we have now we're using. And we also have the Islamic calendar, which is used by some of the cultures actually, which is a lunar calendar. And then you have a hybrid of a lunar and solar calendar. And the word month is actually coming from the motion of the moon. Okay, so that's what the word month itself is. So that's Unit 9. So we're going to dedicate that to Wednesday. And then also we have a lab tomorrow. So tomorrow's lab is going to be a long lab. So I want you guys to arrive early. I know a few of you were not present last time. I know some of you are not taking the lab, so you're not concerned with this thing in here. For those who are not sitting in the lab, never mind. For those who are sitting in the lab, we have a lab tomorrow, and it deals exactly with the topic that we were talking about today. There is a car alarm outside. I'm sorry about that again. So there's all kinds of disruptions. Sorry about that. Anyway, the point being in here is it deals with the solar day and the sidereal day. But it's kind of a long way of doing also this one, because you will be tracking the sun throughout, first of all, the year and some other dates in the year, and then you'll be tracking it here and there, trying to find all of this information, and then also tracking Arcturus, which is a star, and you're going to do all kinds of things. I'm sorry, the first lab is on the motion of the sun, so it's all about the sun and where it's positioned. So it's actually the first part that we were talking about, the motion of the Earth around the sun, the ecliptic and things like that. Actually, the next lab is the one that deals with the lunar, with the solar day and the sidereal day. But those two labs are connected actually. So please come arrive in time and make sure you don't miss these labs, because some of you, like as I said, were not present in the previous lab. And that lab is not actually a requirement. In a sense, you're not supposed to be submitting its lab report, but this one is. It's going to be graded. Okay. For those who are not sitting in Astronomy 125, then this discussion is not important to you, so it's fine. Sounds good, everybody? But even if you're not in Astronomy 125, the project is still due. So it's a hands-on, and you're going to do it. It's part of your grade anyway. Sounds good, guys?
Yeah.
Okay, I will see you guys Wednesday in the same time, okay? And hopefully we'll resolve all of these technical issues. Thank you.